In this video, I'll demonstrate the use of ANSYS Fluent to set up and solve a thermo-fluids case using the Monte Carlo radiation model. The Monte Carlo model is a statistical radiation model that tracks a sample of photon histories through the system. With enough photon histories, a good estimate of the desired physical quantities can be obtained. It's especially suited over other available methods for modeling collimated beam-type irradiation. This case uses an automotive headlamp geometry modeled in an air volume. Solar heat flux is given as an input and the radiation is modeled through the air volume, front cover, and lens. This is precisely the collimated beam-style irradiation in which the Monte Carlo model excels. The goal of the simulation is to predict the location of any thermal hotspots which occur from the solar rays being focused through the lens of the headlamp assembly. This is a common occurrence for cars parked in uncovered areas or stopped on busy highways for a long period of time, and can cause damage to components due to thermal expansion or the burning of plastic components. At this stage, the geometry has been imported, and the materials have been set for each cell zone. The boundary conditions have also been mostly set. I'll be walking through some of the important settings needed to run the simulation. Since this is a thermal simulation, I'll start by enabling energy and opening the radiation dialog box. As I mentioned, I'll be using the Monte Carlo radiation model for this simulation due to the nature of the radiation. I'll set the energy iterations per radiation iteration to 20 and target number of histories to 100 million. This roughly determines the number of photon histories that will be tracked through the system. It should be noted that these settings are case-specific. In general, you should start with a lower number of histories such as 100,000 and increase from there while monitoring how the solution develops. I'll be modeling the radiation as gray. In the cell zone condition task page, I'll open the fluid, lens, and outer lamp cover zones to enable participates in radiation. This will allow modeling of the rays into and through the headlamp assembly. And for the corresponding lens and outer lamp cover boundaries, the semi-transparent BC type is used, again so the rays can enter the headlamp assembly. The rest of the surfaces such as the rim bezel shown here, inner bezel, and seating rim are modeled as opaque and participate by absorbing, reflecting, and emitting radiation. There are 6 bounding walls of the air volume, of which one is specified as the inlet. They are all held at an ambient temperature of 25 degrees Celsius. The inlet, however, will also have a boundary source enabled, with a direct irradiation of 1200 watts per meter squared. I'll also specify a beam direction to capture the effect of the sun's rays not entering the headlamp exactly horizontal. Moving to the Solving tab, I'll open the Solution Methods panel and choose Coupled for Scheme. I'll also enable pseudo-transient, which applies under relaxation to aid in the robustness of the solution. I'll also open the Advanced Run Calculation task page and set the fluid pseudo time step to 1000 seconds. The solid time scale factor of 10 will increase the time step in the solid zones. I'll set the number of iterations to 2400 and click Calculate to start the solution. The solution is now complete and the residuals are quite low, meaning the solution is converged. So I'll move to post-processing. I'll create a new contour of temperature on the inner bezel and we can see the effect of the focusing of the sun rays, with a hotspot almost double the temperature compared to the rest of the surfaces. I can also display the outer cover and lens to give an idea of how the radiation is focused through the headlamp assembly. With this information, a structural analysis could also be performed in ANSYS Mechanical to determine if the resulting thermal stresses are acceptable. And this concludes this demonstration showing you how to use the Monte Carlo radiation model to simulate a collimated beam-style radiation case in ANSYS Fluent.